Okay, P1, conservation dissipation of energy test, 45 minutes, 41 marks. Question 1. When you transfer energy to a shopping trolley, the amount of work then depends on the force used and the distance moved. So here we want to find out the unit of energy, which is joules, force, which is newtons, distance, which is meters, and work done, we know is energy transferred. So it's the same as the first unit, joules. Question 2. Here we've got a person using a stair lift to go upstairs. Stair lift is powered by an electric motor. A Sankey diagram shows the energy transfers taking place. We know 5,000 joules goes as electrical input. 2,000 out of those 5,000 goes as useful energy in lifting the person up the stairs, and the rest of it, 3,000 out of the 5,000, is wasted. The question is, the electric motor wastes energy, and that is as heat and sound energy. Part B, use the correct equation to calculate the efficiency of the electric motor. Well, the efficiency is the useful energy over the input energy. The useful energy, I've underlined useful, that's 2000 divided by the input energy, and the input energy is the input electrical here, 5000, and 2000 divided by 5000 gives us a decimal number. That's okay to leave efficiency as a decimal, 0.4, but we can also leave it as 40%. Question 3. Here we have got 4 different examples: bent metal ruler, stretch bungee cords, springs on a playground, and a molded plastic model car body. So which objects are storing elastic potential energy? So objects that stretch and return back to their original length. So if that's kind of bent, it's not really stretched. That there is molded plastic, that's not really going to bend or stretch either. So here we've got a spring which we know stretches, and bungee cords, just like rubber bands, stretch as well. So that's B and C, 1 mark for B, 1 mark for C. And this explanation, we know that they both stretch, but they return back to their original length. So this needs to be in your answer. Okay, so they both return to the original position once that tension is removed. And what I mean by tension is force. Okay, so that's your 3rd mark. Part B, we've got a spring that is being extended by some weights. We've got a pointer that tells us the position of the bottom end of the spring, and that points to the ruler. Okay, and here is some data that is collected. Rather than it being in a table, it's on a graph. Okay, so we got weight here, and we know weight is measured in newtons, so we can actually put that there, which is going to help. Now, these red lines are reflective of some of the answers which are coming up. Now, weight is a force, and it is measured in newtons. Weight is not mass, and it's not measured in kilograms. Okay, mass is measured in kilograms, weight is measured in newtons. What is the range of weight the student use? So normally this data is in a table, but as it's a graph, we can see that the weights start off from 0 and go to 5. So if every point that has been plotted refers to a weight. So they use 1 Newton, they use 2 Newtons, they use 3 Newtons, 4 Newtons, 5 Newtons. So the range of weights could have been from 0 to 5, or from 1 to 5 Newtons was used. So how far does the pointer move when 4 units of weight are added on the spring? What I mean by 4 units is 1, 2, 3, 4 units of weight, and we go 4 up and across is above 15, not 15. It's one square above 15. From 15 to 20, it's five small squares, and that's five from 15 to 20. So each small square is worth one. So that's 16 centimeters. And the final question here, the student ties a stone to the spring. The spring stretches 10 centimeters. What is the weight of the stone? It's 2.6 newtons, but your paper is not as clear as mine, so I've given you the benefit of the doubt. Okay, so if you go to 10 centimeters, you go across and down, that's somewhere in between 2.4 ish and, well, it's 2.5, 2.6, I would say, maybe even 2.7, but that's closer to 2.6 newtons. Okay, so don't forget to put your units with the values. Question 4. A cyclist accelerates from a set of traffic lights. The driving force of the back tire on the ground is 250 newtons, and they travel 5 meters. What's the work done? So remember the formula: work done is force multiplied by distance, and that's 250 as the force, and the distance is 5, and that's 1,250 joules of work is done to move the cyclist, accelerate the cyclist. The next mark is the next set of marks is what happens to the energy transferred by this force. Okay, so what's happening? It's a cyclist which is accelerating, okay, speeding up. So this work that is done by the person in pedaling is making the bike faster. So that is increasing the bike's kinetic energy. Okay, and because the bike is in contact with the ground, you've got some friction between the ground and the tire, and that converts into thermal and sound energy to the surroundings. So one mark for mentioning that there is an increase of the kinetic energy, and one mark for mentioning heat and sound to the surroundings through friction of the wheels. Question 5. So here we've got an elastic band, and it's key to note that the elastic band is 30 centimeters long. Now the table is 80 centimeters high. How do I know that? Okay, so here from the graph we can see that the height from the floor in centimeters, it starts off at 80 centimeters from the ground. Okay, so we know that that's how high the table is, and when the elastic is just hanging there, it's 30 centimeters from there. Okay, so the first question is mark on the graph a point labeled F where the weight stops falling freely. What does the word freely mean? It means that it stops falling freely, means that the point where the elastic band starts to stretch. Okay, that's when the elastic band will start to slow the object down. Okay, so that's as soon as the elastic band starts to stretch, it starts to slow the object down. So it's just at the point where it reaches 30 centimeters, and that will be, if that's 30 centimeters, that will be 50 centimeters from the ground, just before the elastic band starts to stretch. And that point is labeled F there, and if you go across, that's 50. I mark on the graph a point where the weight finally comes to rest. So we can see here time. The object doesn't really move and change in height all the way throughout here. So you can put S anywhere along this section here. And the last point, mark 2 points on the graph, each label them where the weight is momentarily stationary. Okay, so what's happening is this object is going to be dropped. This elastic is going to stretch, and what's going to happen is the weight is going to start bouncing up and down. Okay, so where does the weight momentarily come to a stop? The weight will momentarily come to a stop at the bottom when the elastic band is fully stretched, and at the top where it comes to a certain height and then it falls back down and it bounces up and down. Those points could have been here, 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 and they are the top of the bounce each time. Question 6. Show clearly how you work out your answer. So what we are trying to do is we're finding out a power lifter lifts 180 kilograms from the floor above his head by 2.1 meters. We know that the gravitational field strength is 9.81, and the use the correct equation to calculate the weight of the bar. We know the formula, we have to remember it. Weight equals mass times gravitational field strength. Mass is 180, gravitational field strength is 9.81, and that is 1766. So you're wondering, when do we use 2.1? 2.1 is for later on in the question. So the power lifter uses a constant force to lift the bar a distance of 2.1. So here comes that distance. And we have got, use the correct equation to calculate the work done by the power lifter. So what's the formula for work done? Work done is force multiplied by distance. Okay, so we know the distance is 2.1 meters, so I've written 2.1 underneath that. And the force in this scenario, because the object is being lifted vertically upwards, the force, what we are doing is countering the weight. Okay, so that will be the weight in this scenario, 1766 times by 2.1, and that is 3708. And its work done is energy transfer, that's in joules. So I've written joules there. Now, the next question is, at the end of the lift, the power lifter holds the bar stationary, so it doesn't move above his head for 2 seconds. How much work is done during these 2 seconds? 0 joules of work is done, and the reason is because the object is not moving. And as we've seen here, the work done calculation is force times distance. So if the distance moved is 0, then the work done is also 0. And that's why you need to mention here. Since the distance moved equals 0, therefore no work is done. That is key there. You need to write that down. Therefore, no work is done. Okay, so that should have written there. Okay, now question 7. GPE equals mass times gravity times height. So we've been asked to calculate the GPE for when the diver falls 4 meters or dives 4 meters from the platform. The formula for GPE is mass times gravity times height. Okay, and the mass is given to us as 50 kilograms. The gravitational field strength is given as 10, not 9.81, but we use the value that's given, 10. And the height, as we've mentioned, the above the below the board is 4 meters. So it's 50 times 10 times 4, which is 2000. And the unit, don't forget, joules. So how do you get the mark? 1 mark for the formula, 1 mark for the calculation, 1 mark for the answer, 1 mark for the unit. Next, kinetic energy is what we need to calculate. And we know the formula for kinetic energy is half times mass times velocity squared. Do we have the mass? Yes, we do, 50 kilograms. Do we have the speed? Yep, 8 meters per second. That's the speed when the diver enters the water. Okay, so what is the kinetic energy for the diver when they enter the water? That's 16,000 joules. So it's a half times 50 times by 8 squared. So 16,000 joules. 1 mark for the formula, 1 mark for the working out, 1 mark for the answer, 1 mark for the unit. Now, notice that when the diver falls, they lose 2000 joules of GPE. And at the bottom, when that GPE is lost, only 16,000 joules of that 2000 is now kinetic energy. So the follow-up question is, why is this different? Why is the 2000 joules different to the 1600 joules? One of the reasons you could have written is that you've got a discrepancy of 400 joules. Where is that gone? Mentioning that, I would say merits a point. And then Where is that energy gone? You could argue that some of the energy has been transferred to heat and sound to the surroundings. Okay, now alternatively, I haven't written it down. You could have written that the diver is jumping. So it's not really 4 meters, it's higher than 4 meters. So that GPE is incorrect. And the also when the diver falls, they don't just fall, they maybe spin and turn. So the kinetic energy, the rotational kinetic energy, needs to be factored in as well. So that's the reason why they could be different as well. Okay, and finally, question 8: the connect. You've got a theme park ride moving left to right, left to right, left to right, swinging. GPE is converted into KE, KE back to GPE, and keeps on doing that. Write down the equation for kinetic energy, and here we have the equation: half times mass times speed squared. Now, what it says is, as the boat swings from position A, which is this position, to position B, the child gains. So when the boat goes from here to here, so GPE is lost and it's converted into kinetic energy. How much kinetic energy has been given to us? Question: 5,070 joules of kinetic energy. Okay, now it gives us the mass as well. So 60 kilograms is the child's mass, and what we try to work out is calculate the speed of the child as the boat passes through B. Well, we want to work out speed. We've got the mass, which is 60 kilograms. We've got the kinetic energy, which is 5,070 joules. Now we need to rearrange to get speed equals. Now, the kinetic energy triangle, put K at the top, half mass speed squared at the bottom. V we've written for speed, and we want to get V squared equal, so cover that up. K is at the top, you got the divide sign, and half and M at the bottom, and because they're at the bottom, the times. So V squared is equal to Ke over half times M, but we need to get rid of the square, so we square root the whole lot, and it's kinetic energy over half times M, which is 5,070 over half times 60. Root all that, and you get 13 meters per second. Okay, so 13 meters per second. Now, part C is a sketched a graph of how gravitational potential energy of the child changes as the boat swings from A, B to C. So what's happening here is, as the boat is moving, they are at this height to begin with. Okay, so you can argue there's the height there, and then the boat is at this height here. So it's fallen in height and lost GPE as you've gone from A to B and gained kinetic energy. Okay, and then from B to C, you've got that kinetic energy, and now what you're doing is you're going back to that higher position in height, and all that kinetic energy is converting into GPE. Okay, now here we've got in the graph, we know that we've got 5,070 joules of kinetic energy was gained when the boat reached this position here. Okay, so 5,070 joules is the amount of GPE that the boat had to begin with, you can argue. So you say gravitational potential energy in joules is what we're looking at. We're not looking at the kinetic energy. So in position A, we've got maximum GPE. Okay, and in position B, you got minimum GPE, and then you got maximum GPE. So the GPE goes down as the object goes into position B and then goes back up. So here we've got, starting off at 5,070. A lot of students mistaken that 5,070 to 5,700. So 5,700 is up here. So 5,070 is down here. Five small squares. Each small square is worth 200. And so that's 5,070 somewhere over here. And then we get to point B, all that GPE decreases, and then we go back to point C where the GPE increases. Okay, you could have said that the GPE is slightly less because of air resistance, so the boat doesn't reach the same height as before. So heat and sound has been transferred to surroundings. You could have argued that, but it's absolutely fine to bring it back to the same point. Do not go beyond C, because it asks from A to B to C. Okay, so if you went beyond C, you should technically do something like that, because it continues to repeat. Okay, so maybe something like that there. Okay, right, and that's the end of your test.